In Chapter 3, Section 5, we need to solve systems of linear equations in two variables, and that brings us to the California State Standard for Algebra 2, number 2. We're going to solve systems of linear equations using a couple of methods, substitution, graphing, and then later in the year we'll come back and pick up matrices. And for now, we're going to look at graphing so we get a visual idea. We're going to do the substitution method, and then we're also going to do something which could be called linear combination, or it's also known as elimination or addition. And then we'll get back to matrices in a later chapter. In the graphing process, when you're graphing two straight lines on the Cartesian plane, one of three things will happen. The two lines will intersect at one point, and that one point is your one solution. The graphs will be parallel and never cross, in which case there are no solutions. Or the third possibility is that the two graphs will coincide, or in other words, be the same line. In that case, every point that's on those two lines are your solutions. There's an infinite number of solutions, but it's only the points that are on that same line. For vocabulary words, if there is a solution, we say it's consistent. If lines intersect at one point and there's only one solution, we say it's consistent independent. And then if they're the same line, it's consistent dependent. And then finally, if it's parallel lines and there's no solution, we say it's inconsistent. So those are the vocabulary words for that. So let's try to practice some of this information by graphing these two lines. If we start with y equals x plus 1, that crosses the y-axis at 1. Remember, slope-intercept form tells us the y-intercept is 1 and the slope is 1. So where the y-axis, where we cross the y-axis at 1, we go up 1, right 1, up 1, right 1, and connect the dots. For the second line, the y-intercept is 3. So we're going to locate that point, the y-axis at 3. The slope is negative 1, so we're going to go down 1, right 1, down 1, right 1 as many times as we wish. And the two lines do intersect at a point. And what we need to know is to find out exactly what that point is. And in this case, that's the point 1, 2. That is my solution. So there is a solution. It's consistent. My solution is 1 point. We say it's independent. All right, let's look at the second scenario that'll happen when we're graphing two lines on the same x and y axes. So let's start out with the first graph. Has a y-intercept of 1, so it crosses the y-axis at 1. Has a slope of 2, so we're going to go up 2, right 1, up 2, right 1, and connect the dots. Second line crosses the y-axis at negative 3, and also has a slope of 2, so from there up 2, right 1, up 2, right 1. And I think you can see already, just from the equations, that the equations have the same slope, which means you're going to have parallel lines, which means they'll never intersect. There's no solution, or we use the vocabulary word inconsistent. All right, let's take a look at the third possible scenario. So let's graph these next two on the same x and y axis. And the first one, I'm going to use a little trick here. It's called graphing using the x and y intercepts. If I replace x with 0 and solve 2y equals 8, we know that y equals 4, and that tells me my graph will cross the y-axis at 4. If we put in a 0 for y in that top equation, then we see that 4x is equal to 8, therefore x is equal to 2, and that's where my line crosses the x-axis at 2, the x-intercept. So that little shortcut, putting 0 in for x, finding out where it crosses the y-axis, putting in 0 for y, finding out where it crosses the x-axis, that's called graphing using x and y intercepts. So we connect the two dots, and there's our graph. The second line crosses the y-axis at 4, has a slope of negative 2, down 2, right 1. And yes, you can see that those two lines coincide. They're the same line. There's an infinite number of solutions. We cannot list all infinite ordered pairs, so we just write the equation in slope-intercept form and say that every point on that line is our solution. And since we have a solution, it's consistent. And since there's an infinite number of solutions and they're actually the same line, we say that it's dependent. Alright, so visually we can see that the two lines intersect at one point, are parallel, or that they're the same line. With that in mind, let's try some non-visual methods for solving equations. Substitution is a very useful method if one of the variables has a coefficient of 1, and you get that variable by itself. This problem is actually set up for us. If x plus y equals 5, x is equal to y plus 1, why don't we take this y plus 1, which is the same as x, and in the top equation, everywhere we see the x, replace it with y plus 1. If we do that, then we'll have one equation, one variable we can solve. So let's take this x as y plus 1, replace the x with the y plus 1, and simplify. So 2y plus 1 equals 5. Subtract 1 from both sides. 2y is equal to 4. Divide by 2, and y is equal to 2. Well, that's only half our answer because we need an x value. So we're going to substitute again in part 2. We know that x is the same as y plus 1. Y, we found out, is 2. So 2 plus 1 is equal to 3. X value is 3. So we have our solution. X is 3 and y is 2. And we have a solution, so it's consistent. My solution is 1 point, and we say, therefore, it's independent. So that's the method of solving systems of simultaneous equations known as substitution. For linear combination, what we want to do is to try to add the two equations together to eliminate one of the variables. That's why sometimes it's called the elimination method. And in this particular case, you see if we add the two equations, nothing gets eliminated. So what we might have to do is to multiply one of the equations, or maybe even both of the equations, by some number to eliminate one of the variables. In this situation, if we multiply the top equation by -2, then we'll have -6y and a positive 6y. When we add them together, the y's will drop out. We could have chosen other numbers, or we could have chosen to multiply both equations. But this will be the simplest. So multiplying the top equation by 2 gives me -6x minus 6y, and don't forget to multiply this constant by the -2 equals -30. Alright, we're all set to add those two equations now. When we add them, -6x plus 2x is -4x. -6y and positive 6y drop out to 0, which was our goal, to eliminate one of the variables. And -30 plus 22 is -8. Let's continue to find out what x is. So divide both sides by -4. X equals 2. That's half our solution. We need to know the y value. For the second half of this problem, part 2, we're going to do the substitution method. Choose either the top equation or the bottom one. Doesn't matter which equation we choose. Whichever one we choose, we're going to substitute 2 in place of x. So to simplify that, 3 times 2 is 6. Subtract 6 from both sides, and 3y is 9. Divide both sides of the equation by 3, and y is equal to 3. And since we have now our x value of 2 and our y value of 3, we know our solution is the ordered pair 2, 3. We have a solution, so it's consistent, and my solution is 1 point, so we can say it's independent. Alright, let's look at this last system of simultaneous equations. And in this case, there is nothing I could multiply 3 by to get 5, or 4 by to get 5. So we're going to have to multiply both equations by some number to drop out one of the variables. And in this case, if we multiply the top equation by -3, bottom equation by +5, and it could have been +3 and -5. But what we want to do is to try to eliminate x here. I could have also multiplied the top equation by something to eliminate y. So we could have done 4s and 5s. 5 for the top equation, 4 on the bottom, and then just drop those out. 3 and 5 are the ones we chose in this particular case. So let's multiply those through. And the red equation here, 3 times -5x is -15x. then minus 12y. Don't forget to multiply that constant. 11 times negative 3, that's negative 33. And the blue here will multiply out the 5. So that's going to be 15x minus 25y equals negative 115. Don't forget to multiply that constant by the 5 also. Now when we add, the x's drop out, which was our intended purpose. Negative 12y and negative 25y is negative 37y. Negative 33 plus negative 115 is negative 148. And we can divide both sides by negative 37 to find out that y is positive 4. Well, for x, we'll substitute in either equation, the top one or the bottom one. So let's use the top one. 5x plus 4y equals 11. Instead of y, we're going to substitute in the fact that we found y to be 4. So 4 times 4 is 16. Subtract 16 from both sides. 5x is negative 5. Divide both sides of the equation by 5, and we find out x is negative 1. So our solution is x is negative 1, y is positive 4. We have a solution. It's consistent. It's 1 point. It's independent. And that's our first look at solving systems of simultaneous equations using graphing, using substitution, and using this method called linear combination, or sometimes we call it elimination.